What's up, guys? Welcome.
Hello and welcome back to Calculus3 again. Now with the brand new updated Windows. Last time where we left off was defining, well, first we did one triple integral to find the volume of the box, which was very easy. And then we started talking about the more general case, which allows for planes and surfaces to be integrated into integrals, shapes. So now I have this triple integral, and we see that dx is at the end. So if we have dx at the end, I will have a and b for those limits. And then now there's lag over there. Great. These functions here, g and h, have to be in terms of x. And the function at the end are in terms of x and y. So now, just as an exercise, I will ask you to write the formula. Well, that's just the name, function g. Could have said it was the next letter in the alphabet. You're welcome. All right. Well, what can I say? I try. So let's see. How about dx, dz, dy? So again, use g's, but g and h. But I'm interested what goes in these parentheses. If you are understanding this at all. So populate these parentheses, put the limits on the outer, you know which letters should go there. If it's dy. Let's see. So how would this go? Try to do this on your own, and then I will fill it up.
You already did.
I didn't, because what variables go in here and here and here and here, right? The letters, you can put whatever function you want. And these letters, what letters you put there? For y.
But y is only in terms of x, so shouldn't. Y is not in terms of x, but independent of each other.
Z is independent of
Well, this is all right.
You have three independent variables.
Yeah, I don't got that.
Take it out. Put it in the microwave. The battery captures the microwave.
It's really tiny waves. Like they're trying to say hi to their friend, but they can't. Their friend can't see it. So
Let's go, guys. Come on, populate the parentheses. Let's go. What do we have?
I infer a structure. xc, and then that is
Right.
y. I don't know. I have no idea.
So you said it's easy.
Yeah, it's easy. It's what I said.
And then you'd have to have y
So
here.
how is it easy if you have no idea?
I don't know.
Right.
Because,
It's hard.
well, hang on. Can the lowercase g, lowercase h just have any one of those two variables? Okay, great.
There's specific ones.
No.
No, that's not 1986.
Throwback.
Why is it?
Yeah,
Why?
Yeah, that's why. Also, it's just a brick. It doesn't actually work. But I'm not
You-
gonna.
This is bad. This is wrong.
Wait,
X
what?
over I.
The universal algebra. It's all like intersects.
Looks wrong.
That's not how you deal with reality.
That's like extreme.
Somebody doing that in my auto shop in high school. No, they weren't doing it in the auto shop. It was one of the classes next to auto shop. It's like they did the one time, and then it's just like,
Yeah, I checked it. I checked it.
And he goes, okay. And then after the second time, he goes, yeah, okay, it was funny the first time. Now it's not. He goes, oh, you think I
Confiscate all your phones and
Close the list here and then
HTC.
Why do you-
You guys HTC. Pull out all your phones. And I had like a iPhone. I'm like, I'm good.
I'm good. I have a track phone.
And note how I called it the lid. Here we go.
Yeah, mine is supposed to be able to do that, but it doesn't work for us.
The outer integral is in terms of y, so we are going to place c and d. Usually we use a and b for x and c and d for y. Now, the middle integral belongs to dz, and when we are integrating dz, the only available variable that is yet to be integrated afterwards will be y, so these must be y's. And then when I'm at the most inner integral, I am integrating out x's, so these are y's and z's.
Is there any difference between Y and Z and then Z and Y?
No, they're all independent of each other. So you can write it z, y, z, or zy. We usually, right? So let's talk about setting up these integrals. So let's create some kind of a wedge. Oh. So now we have that this top is z equals to 6. because that's a 6 elevation right there. This is where our origin 0, 0 is. And this one over here is xz plane, clearly y equals 0, right? The one on the bottom is in the xy plane, so clearly z equals 0. The one in the back is in yz, which means x equals 0. And the one on the side, right, maybe should I say front? That's what we can see, is given as 4 minus y equals 4 minus 2x. So set up triple integral. Mechanical engineers, there's your life right there. So your job is to set these things up, and computer will integrate and do other things. So where do I begin? Well, first order of business, after we put 3 integrals down, and we're looking for volume, so there will be nothing here. You can put number 1 if you want to. We first have to figure out whether we want to do dx dy dz, or dz dy dx, or dz dx dy, or dy dz dx, or right? You get the idea. So which one are we going to, which order are we going to use? Observe that we have y as a function. So definitely dy cannot go on the outside. So that's one of the things that you have to understand right off the bat, that if one of these, so I'm going to start with dy because I'm just going to get rid of it, right? And then let's say dx and then dz, because none of the other ones have functions. Now looking at the z is easy, right? The outer goes from 0 to 6. You have a plane, which is the floor, and you have a 6, which is the ceiling. So those are there. Now y, if you look carefully, which is the most inner one, goes 0 to 4 minus 2x. And x travels from 0 to what value? 4. No, 4. 2. Now why 2?
That's when the line crosses the x-axis.
Which line?
4 minus 2x.
4 minus 2x, so y is equal to 0. And when y is equal to 0, to get y equal to 0, x needs to be 2, because then 4 minus 4 is 0. So what was tricky? This was tricky, and figuring this out because you're still new with this stuff. So I'm going to redo this, all of it, one more time. I notice that y has the equation to it, which is the reason why I'm going to put dy on the inner side. And its limits are immediately 0 to 4 minus 2x, because those are the y's that I have. The rest of the order doesn't matter which way it goes, whether you're going to do dz dx or dx dz, because they both have just numbers. So dx dz is what I used. And now the outer integral z, if you look carefully, floor to ceiling is 0 to 6. And now we have our x values. Now we see that x, we already have one equation for x, which is the equation all the way in the back, x equals 0. So we are going to use that one as the bottom. And now the big part is what goes there. Well, if you observe this equation here, that equation will tell you how far x gets to go on the x-axis, because that equation is when x has to end. Now, that happens when y is equal to 0. To get y equal to 0, x must be 2. And now you just do 3 Calc 1 problems. Do the inner integral first, then do the middle one, and then the outer. Is actually on my computer appears to it's offline, but
Oh, now it's back. It just keeps saying.
I ran into one of my Calculus 1 students from last semester, and she told me she's watching my streams live, getting ready for Calc 3 for next semester. So I guess she's taking Calc 2 over the summer. I'm not sure if this works now.
Oh God, no, no.
All right, looks like we're back in business. Is the stream pick up?
I think so.
All right.
There we go. Move your mouse around a bit, or I don't know.
Well, we are going to. No, there's a lag, so delay. So you should see.
It's buffering. And now it's offline. Either your stream's offline or it's just not letting you launch it live.
I'm not sure.
Now it's back.
Everything looks okay over here. It just keeps. I don't know. It keeps thinking. All right. So let's continue. You have the previous semester, this lecture previous semester, so go on my YouTube channel, just scroll down for 15 years and you'll find another one. The next order of business is to take a look at a more complicated shape whose calculation is going to have the actually like this. Yeah. So let's take a look at two shapes intersecting. These are going to be the paraboloids. We have paraboloid y equals x squared plus z squared, and the paraboloid y equals 16 minus 3x squared minus z squared. So this one has circles and this one has ellipses. So what are we going to do? Well, first of all, graphing these, will give us, we are wrapping this on the, which axis? Which axis is special? Y, very good. So y-axis is special, and since this one is elliptical, a little bit tricky to draw, but so something like this.
What is this?
Well, one of these is circular. The other one is elliptical. So they are not going to have an edge, circular edge that meet at. They will meet, the one shape will kind of probe deeper into the other.
Oh, this is two different shapes.
Yes,
Oh.
yes. So you have your blue and you have your black on this side. So now, what is the issue here? First of all, when I am setting integrals up, right, I need the triple. I need to figure out which one is the one that will carry functions. And that one goes on the inside. I hope you guys see that that's dy, because it's y equals and y equals, and they contain all of the x's and z's as well. So dy must be the most inner one. And then we have a choice of dz dx or dx dz. So this one here will carry all of the variables. That one carries all, that one works with all three variables. This one works with two variables, and this is only the one variable, the calc1 at the end, right? So if you look at y's, right, y is in terms of two variables, which is the reason why y is the one that it's going to go first. And then you go close by, and then 16 minus 3x squared minus z squared there. And now you have a choice to put either xz or zx. Yes?
How do you know that x squared plus z squared is on the bottom?
This is where the
Oh,
home
okay.
is, further away, which is where 16 is. Further away is the black, and then closer by is blue, right? So far minus close. On the special axis. See, that's all of the concept so far. All right, the next order of business is, you can think of the first two as the domain. And the domain you get when you take a flashlight, you shine the light And that will create an image over here on the domain plane. It's either the floor or one of the sides. Equation of this one is going to be these two integrals here. Guys, this is not easy. You have to understand a lot of stuff here. To get this equation, we are going to set the two equations equal to each other, which means x squared plus z squared is going to be 16 minus 3x squared minus z squared. So it gives me 4x squared plus 2z squared equals to 16, which is 2x squared plus z squared is equal to divided by 2, 8. And when I divide through by 8, I get x squared over 4 plus z squared over 8 equals to 1, ellipse. I mean, we did not expect anything else, but we got that.
Why did you say that?
I'm sorry?
Why did you set those two equations?
I need to find the equation of this line in the domain, the shadow, because that's the bound on the. That's the bound that will give me limits for the first two integrals. So now, if you are looking at this, your domain looks like this. This is your x, this is your z, and then z will have 8, so it looks like this. What does this mean? This equation here, we can solve it for either x or y, but what's important is to know what these points are. And you know that from equation of the ellipse. This is negative 2, and this is positive 2. And this is negative 2 root 2, and this is positive 2 root 2. Now you see how x's have easy values. So let's keep x on the outside with its negative 2 and positive 2. So if that's my dx, then dy has to be the top function minus the bottom function, which is when I flip this equation and solve this equation for z. So z equals square root of 8 minus 2x squared, and it's a plus and a minus. So minus gets, the bottom goes with the minus, and the top with the plus.
Why couldn't you have like x first, x before z?
I was about to say, now let's do xz because we can. Yes?
Why do you need to find z an equation for z rather than just using the 2 root 2 and negative 2 root 2?
Because it's not a box, it's an ellipse, right? If you are to use the numbers, you will be working on a rectangle instead of the ellipse. Guys, that was an excellent question, and I hope you heard the question. The question was, why, for the blue one here, why did we use negative root 2, 2 root 2, and positive 2 root 2? And the answer to that is because it's ellipse, it's not a box. If it was a rectangle, you would be using negative 2 and 2, and negative 2 root 2 and 2 root 2. That would be a box. But because it's ellipse, you have from -2 to +2, and look, this top is not writing a horizontal function 2 root 2. It's writing this arch, which is from the ellipse, and that arch is given by this equation. And the bottom is writing the negative arch, so that's why it's those two. So it's gonna take some time for you to sit down and sort through this stuff. Now solving some of these integrals, you know what I mean. We have to learn how to do cylindrical integrals and spherical integrals so that some of these integrals can be converted and properly computed, easily computed actually, in those frames. The next question was, can we actually interchange x and a z? And the answer is yes. You can have this dy, dx, dz, but that will obviously change the limits on the first integral, because the first integral would now be from negative root 2 to positive root 2, 2 root 2. And the middle integral would also change, because you would have to solve this equation for x squared rather than for z. So it's possible. It's just going to be uglier than this, so that's why we don't do it. All right, let's take a look at the homework. They have many wonderful shapes. Let's do, let's say, 2 examples or so. Problem 17 looks good. So we have a cone. You have ice cream, okay? You see the spherical ball of ice cream on top, right? And you see a cone. Except it's exaggerated, right? So equation for the ice cream part is x squared plus y squared plus z squared equals to 8. And the equation for the cone is z equals square root of x squared plus y squared. What's the volume? Try to set this up on your own. I give you 21 seconds. Go. Okay, so what is the order? dz, dy, dx. Okay, I like that. Yep. So as we start, I will remind you that we shine the light from the top and we see the domain over here. And we see that the domain is going to be on x and a y, which means that x and y will be the last integrated, which means z is integrated first. We can also see that z needs to be integrated first because this equation is given as a z equals everything else in terms of x and a y. So as I'm setting this up, this triple integral, I will start with the dz and then dy dx, and I'm using dy dx just because Nick said so. Now I'm going to use dz. The bottom is the cone, which is the square root of x squared plus y squared. And the top is going to be the square root of 8 minus x squared minus y squared. So that's the top when you solve the equation up there as the sphere. So now we are looking at the domain xy. I have a circle, or something that I hope it's a circle, and I need to figure out what it is. The way I do this is I set the two equations equal to each other, but I can also plug one equation into another, which would actually be very convenient here to plug this right there and kills the square root, and we can combine like terms. So that's, in my opinion, better. So we'll have x squared plus y squared plus square root of x squared plus y squared squared equals to 8. These guys cancel, so 2x squared plus 2y squared equals to 8. X squared plus y squared equals to 4. X squared plus y squared equals to 2 squared. That means that the radius is 2 all around our domain. So the outer integral limits better be negative 2 to 2, because we see that dx, right, which would be, if you are going to draw dx, and now observe that the top is touching square root of 4 minus y squared. Oh, not y squared, x squared. Sorry, kill it. And the bottom is negative 4 minus x squared. So circle always has equations. So just keep setting these up. Hopefully the homework will provide you with lots of examples. And then we can set few of these up next next class as well, tomorrow. We're going to take a short break. And then we have cylindrical and spherical coordinates.